Today I'm going to talk about the communication complexity of payment computation. This is joint work with my advisor, Shachar Dobzhinsky. Okay, so let's start with the preliminaries. Okay, so we begin by introducing the model of communication complexity. When we use this model, we assume that each player holds a subset of the input, and we wish to compute some function on the shared input of all the players. And the question we care about in this model is how many bits do the players need to exchange in order to compute such a function. For example, imagine two players, each of them holds k bits, and we want to know whether their sequences of bits are equal to each other or not. A trivial protocol for this problem is having player 1 send to player 2 all of her bits, and then player 2 already knows her own bits. She now also knows the other player's bits. So she knows whether they are equal to each other or not. So she can send back 1 bit that says equal or not equal. And the total communication of this protocol is k plus 1 bits, and it is known to be typed. A basic fact that we will use later is that the communication complexity of each function is at least the log of the size of its image. And the intuition for this fact is that if just specifying the output takes at least log set bits, then you can't do anything better than this. The functions we're interested in are called social choice functions. Those are functions whose inputs are another n functions, called valuation functions, where each such function expresses the preferences of the players over the alternatives. Since the private value of each player expresses how much he wants each alternative, computing the function might not be so straightforward, since players might misreport their values in order to get alternatives that they want more. And in order to handle this issue, we add payments. And we call a function implementable if for every player there exists a payment scheme such that she maximizes her profit by reporting her true bid and not by bidding some other value. And a social choice function combined with its payment schemes for all the players is called a truthful mechanism. For every function, we use the following notation, CCICF, to denote the communication complexity of computing the function and its payments. Let's see an example. Suppose that we have 3 players, a cat, a boy, and a girl, participating in a second price auction where the item that they want is an apple. In a second price auction, the bidder with the maximum value wins the apple and pays the second highest bid, whereas the other players pay 0. The communication complexity of the function is the number of bits we need in order to output the winner's identity, which is the cat in our case. And the communication complexity of the alternative and the payments is the communication complexity of outputting the cat's name, plus how much the cat pays, which is 20, and how much the other players pay, which is 0. So most of the results I'll talk about today are in single parameter settings, so I'll explain this term. Informally, a function is called single parameter if the valuation functions of the players are relatively simple, in the sense that the private information of each player is just one single scalar. So let's see an example of a single parameter function and also an example of a multi-parameter function in order to understand the difference. Let's begin with the single parameter example. Take a look at a multi-unit auction with additive valuations where the items are 2 identical apples. Note that if we know that the value of blossom for 1 apple is 3, then we know that our value for 2 apples is 6 and that our value for 0 apples is 0. And therefore, a valuation can be expressed using just one number. For the multi-parameter example, we consider a different auction. Again, we have additive valuations in 2 items, but this time they are different from each other. One is green and the other is red. In this case, if the value of bubbles for a green apple is 3 and our value for a red apple is 5, then you can tell that the value for both of them is 8, since the valuations are additive. Now, 2 different scalars are needed in order to express the valuation of bubbles. One for a value for the green apple and one for a value for the red apple. So we get 2 parameters, which is more than 1 parameter, and therefore it is indeed a multi-parameter setting. Now we are ready to present the main question this paper revolves around. And the question which was raised by Fadel and Segal in 2009 is how large can be the gap between computing the social choice function and computing the function and its payments. In other words, how large can be the overhead of payment computation? Now let's go over some previous results. So Fadel and Segal raised the question, showed that the overhead of computing payments is at most exponential. Also, they showed a function where computing the payments has communication overhead of at least 1 bit. And afterwards, Babayev, Blum-Rosen, and Oren-Shapira have showed a function where the overhead is at least multiplicative in the number of players. And our main contribution is that we solved the open question raised by Fadel and Segal by providing explicit functions with exponential overhead of payment computation. First, we showed that even in a pretty simple setting where there are only 2 players with single parameter valuations, there exists a function such that the communication complexity of the function and its payments is exponentially larger than the communication complexity of the function alone. And concurrently and independently, Rubinstein, Saxana, Thomas, Weinberg, and Zhao have found another 2-player function which exhibits this exponential gap. However, the social choice function in their lower bound proof is multi-parameter. In their paper, they also investigate the difference between implementation in ex-post equilibrium and implementation in dominant strategies. Our other results are as follows. So one feature of the function that we provide is that the function's payment schemes have huge images, and this is a feature of our construction and also of the construction in the other paper that I've mentioned. And we show a characterization for 2-player settings that demonstrate that this feature of the proof is essential. The communication complexity of a function and its payments is at most the communication complexity of the function alone plus the log of the size of the images of the payment schemes for 2-player settings. And this characterization made us wonder, could it be that payment computation is hard only when the images of the payment schemes are huge? And we answered this function in the negative by providing a function with 3 players, which is also single parameter, where the number of payments is relatively small, and yet we achieve an exponential gap between a function and its payments and the function alone. Note that those two constructions show 2 different sources of hardness for payment computation. One is the number of payments, and the second one is that payment computation is a case where payment computation requires a lot of interaction. And we admit that our functions are a bit contrived, and we wonder whether payment computation might have exponential overhead also in a more natural setting. And we answered this question by providing a welfare maximizer in a multi-unit auction for 2 players for payment computation as an exponential overhead. And we show and we remind that, as shown by Fadel and Segal, the overhead of payment computation is at most exponential. So those 3 lower bounds are tight. Now let's get to some positive results. For deterministic implementations, we show that in several settings, the communication cost of a function and its payments is polynomial in the number of alternatives, the number of players, and the communication complexity of the function. Those settings include all single parameter settings and some multi-parameter settings, such as convex domains and functions that satisfy uniqueness of payments. We also show that if we compromise on truthful and expectation mechanisms, many functions can be computed with polynomial overhead. I'll just remind that the mechanism is truthful and expectation if a player always maximizes expected profit by bidding a true value. And the upper bound on truthfulness in expectation combined with the lower bound on deterministic payment computation implies that there exist single parameter functions with an exponential gap between deterministic implementations and truthful and expectation implementations. Therefore, we actually now let's show some intuition to some of the proofs in the paper. So let's start with the 2-player theorem. And we recall, let's remind what the theorem is. It says that there exists a social choice function with 2 players where payment computation is exponentially harder than the function alone. And we are not going to present the construction, but we will state some properties of the function and explain why they imply that payment computation is costly. So we constructed a function where the size of L is of Alice's domain is k. The size of Bob's domain is 2 to the k. The number of alternatives is k. And the size of the image of Alice's domain is 2 to the k as well. So first of all, let's show that why computing the function can be done in log k bits. Observe the following protocol. We have Alice and Bob. Alice can send all of her information to Bob using log k bits. And then Bob knows Alice's value, he knows his own value, so he can just apply f to them and send it back to Alice using log k bits as well, because there are only k alternatives. And overall, we get order of log k bits. Now, the other claim is that computing Alice's payment is hard. And how do we prove that? Notice that the image of the payment scheme of Alice is exponential in k, and record that the log of the size of the image of each function, in particular payment scheme, is always a lower bound for the communication complexity. So we get that the communication complexity of the payment is at least k, and we manage to get the needed gap. As we've said before, the hardness of payment computation in this case is based solely on the huge number of payments. Now we will explain why this feature was essential to the proof of the theorem, and we will do that by presenting the following characterization for two-player settings. So the communication complexity of a function and its payments in this case is completely determined by 3 factors. The first one is the communication complexity of the function. The second factor is the log of the size of the image of the payment scheme of Alice, and the third one is the log of the size of the image of the payment scheme of Bob. And note that this characterization indeed implies that the only way to obtain an exponential gap between computing and implementing a two-player function is having the number of payments to be doubly exponential in the communication complexity of the function, because otherwise you can't get an exponential gap between ICF and CCF in this setting. And given this characterization, it is natural to ask, can we extend it to 3 players or more? Or in other words, could it be that payment computation has overhead, which is polynomial in the communication complexity of the function, and log of the size of the images of the payment schemes of the players, which is at most bounded by this. This is what I meant. And we answer this question in the negative, which means that the suggested characterization above doesn't hold. And we show that even if you add just one more player, there exists a single parameter function where payment computation is hard, despite the fact that the payment schemes of the players have small images. So now let's prove that, and we'll repeat the theorem. We'll show that there exists a single parameter function for 3 players, where the overhead of payment computation is exponential, and yet the number of payments is relatively small. It's small in the sense that specifying the index of some payment has no major overhead compared to the communication complexity of the social choice function. And again, we're going to assume uniqueness of payments, and this is only for the talk. We've assumed also uniqueness of payments before. And again, at this time also, it was only for the talk. So the idea of the proof is that you want to create a situation where the alternative chosen depends on the small number of bits, whilst computing the payment requires some global computation. And try to keep this idea in mind while seeing the construction. So there are k+1 alternatives, and the evaluation set of Alice is such that she holds a private value between 0 and k-1, and our value for each alternative is simply her private value multiplied by the alternative. For example, if she holds a scalar 2 and an alternative 3 is chosen, then our value for it is 2, her private value multiplied by 3 is the alternative, which is 6. Similarly, if alternative 4 is chosen, then our value for it is 2 multiplied by 4, which is 8. And Bob and Charlie have pretty fun evaluations. They actually don't care which alternative is chosen, but each of them holds a scalar, which is their value for all the alternatives simultaneously. For example, if Bob holds the scalar 3, then his value for every alternative, be it alternative 0 or k or anything in between, is always 3. The same holds for Charlie. If Charlie holds the scalar 4, then his value for all the alternatives is 4. And note that for both Bob and Charlie, the valuation function VB and the valuation functions VB and VC are actually equal to the private information xb and xe. So we are going to abuse notation and write vb for xb and vc for xe. Also, we will mostly look at the values of Bob and Charlie as k-bit strings, and so we will denote the jth bit of Bob with vbj, and similarly we will denote the jth bit of Charlie with vcj. Now let's present the social choice function, and I will give an example with numbers in order to explain it. Assume that Alice holds the scalar 4.5. Then you can see that the alternative chosen is either 4 or 5. If the fourth bit of Bob and Charlie are both equal to 1, then alternative 5 is chosen. Otherwise, alternative 4 is chosen. And if 2 bits at some index are equal to 1 for both Bob and Charlie, we say that those 2 bits intersect. And now let's see an illustration in order to understand the function pictorially. For the illustration, we're going to expect the function where we fix k to be equal to 4. And we consider the following graph, which we call an allocation graph. Each value of Bob and Charlie fixes such a graph. And let's look at the case where the values of Bob and Charlie do not intersect at all. And note that the x-axis of this graph is the private information of Alice, and the y-axis is the alternative chosen. So first of all, if the private information of Alice is between 0 and 1, then we check whether the bits at index 0 of Bob and Charlie intersect. And if they don't, all the values between 0 and 1 are assigned with 0, and we move to the next bits. The next bits at index 1 also don't intersect. So the values in the interval 1 to 2 are assigned with alternative 1. This is how we proceed until we get this step function. Well, 0 is assigned with 0, 1 is assigned with 1, and so on. Now let's take a look at the different values of Bob and Charlie and see the allocation graph that they induce. Note that if there is an intersection at the first bit, then there is a jump at index 1. Similarly, if there is an intersection in the second bit, then there is a jump at index 2. And again, if there are 2 intersections at the first 2 indices, then we get this graph. Now that we understand the behavior of the function, let's discuss the payment. According to Myerson's lemma, the payment of Alice is equal to a value of the chosen alternative minus the area under the curve of this allocation graph between 0 and our private value xa. Therefore, the payment function of Alice is tightly related to the number of jumps, which is actually the number of intersections. Now we are ready to prove the theorem. So we'll start by showing that the function f is easy. Note that the function can be computed by a protocol where Alice rounds down her private information xa to the nearest integer, and then sends it using log k bits. Afterwards, it is known that the alternative is either the rounded down xa or the rounded down xa plus 1. So in order to know which one is chosen, Bob and Charlie sent their bits at the index that Alice sent. And now everyone can tell which alternative is chosen. Now, note that the payment, which is essentially the area under the curve, depends on the number of intersections between Bob's bits and Charlie's bits. You can see that if there is one intersection, then the area under the curve remains the same. And you can see that it is always the same area under the curve for all those 3 cases. Similarly, if there are 2 intersections, then the payment is always the same, and so on. Now, in order to prove the hardness of payment computation, introduce the function disjointness, which is the canonical hard function of communication complexity. It is a function where each player holds a k-bit string, and the output 1 if the sequences of bits are disjoint, which means that there's no bit which is equal to 1 on both strings and 0 otherwise. And now we will prove that payment computation is hard by reducing disjointness to it. Given 2 sequences of bits, x and y, we can plug Bob's value to be x and Charlie's value to be y, and the payment is different for 0 intersections compared to 1 or more intersections. As we said, disjointness requires at least k bits, so computing the payment requires at least k bits as well. So we have the first item of the theorem, that computing payments is exponentially harder than computing the function. Now it is left to show that the number of payments is small. And the payment schemes of Bob and Charlie are such that they always pay 0 because they don't care which alternative is chosen. So the number of possible payments is 1 for both of them. So clearly item 2 holds for them. And the interesting part is to show that Alice has a small polynomial in K number of payments. Recall that, as we've said, her payment depends on her value for the chosen alternative, minus the area under the curve between 0 and her private information. And our value for the chosen alternative is, by definition, always an integer between 1 and k squared. And similarly, one can see that the area under the curve is also always an integer between 0 and k squared. Therefore, the payment is a subtraction of two integers in the range 0 to k squared. So the size of the image of the payment scheme, according to this formula, is of order k squared. And note that we've shown all three parts of the theorem. We've shown that computing the function is easy, that computing the payments is hard, and that there are not too many payments. Okay. So we've seen hardness of payment computation. So let's go over what we've done. We've seen hardness of payment computation via the number of payments. We've seen hardness via interaction. We remind that we've also shown in the paper that payment computation might be exponentially harder than the function alone for a male welfare maximizer. Also, we have some upper bounds for deterministic implementations and also for truthful expectation implementations. And we also have a third type of results that we don't have time to talk about. Thank you.